Okay, so I wanted to point out that what I will be doing today, which is to talk about the density operator framework, you'll find this discussion in section 2.4 of Nielsen-Chuang. And whatever we've discussed so far about POVMs and this formal proof of how non-orthogonal states cannot be distinguished, etc. That's all section 2.2. In particular, check out box 2.3, where this proof of the fact that you cannot distinguish non-orthogonal states is there. And Nielsen also gives you a problem which wants you to extend that same proof argument that you had for just two states to a set of n pure states. Okay, so you can also take a shot at this problem, those of you who are inclined. Okay. All right. So today what we're going to discuss is, so we discussed an extension of measurement, right? The measurement postulate as was known as you might have studied in quantum theory. We've seen now a more general way of describing measurement. In a similar way, today I'm going to tell you that actually there's a more general way to describe the quantum state. Okay. So far we're used to thinking of states as vectors in a vector space, right? But what we're going to see today is, first of all, that this formalism is not sufficient and we need something beyond that. So first of all, why do we need something beyond that? So take the case of measurement, right? The trickiest part of this theory, right? Now, some of you already asked me, right, as to what is the proper description, right? So what is a proper description of the post-measurement state? And this also ties in with the question of how do you formally describe the measurement transformation? So we saw that this is not a gate, right? This is not a unitary transformation, right? This does not map states to states the way we know it. This does not map vectors to vectors, right? Instead, we had to do this, resort to some cartoon pictures and some arrows and all that. Whereas with unitary transformations, it is very clear, right? So if U is a unitary, then you know that U acting on psi will give you some other state phi, and this is a very valid transformation on the set of vectors in a Hilbert space, right? But now if I want to describe measurement, then the way we did it so far was to, so let's, for example, even just stick to projective measurements, right? And we said that basically the state psi, so let's say you're measuring some observable A with eigenvalues AI, corresponding eigenstates get AI, etc. Then we said that psi will collapse to AI, right? And this happens with some probability P of AI, which is this, right? But how does one, is there a way to formally describe this? So I gave you a kind of in-between answer and I said, think of the projector onto psi, okay? And then think of this action as having happened because of a certain projector Pi, which is simply the projector onto the ith eigenstate, right? And then we could describe the measurement transformation like this, but then we had to normalize this with the corresponding probability, right? But what really is the post-measurement state and how do we describe it? So this post-measurement state, since each realization of the measurement is giving you a different outcome, right? Or rather can give you a different outcome in general, right? Based on a set of probabilities. So actually the post-measurement state is an ensemble. The reason we are struggling to give a formal description for it is because it's not a single state anymore. The post-measurement state actually describes an ensemble. Ensemble meaning a collection of states, rather a collection of possibilities, right? So the post-measurement state is describing an ensemble, and is there a way for us to describe ensembles, right? So what is this ensemble that is associated with this particular example? So with this particular example, the ensemble that is associated with it is this set of states AI, right? So these are all the possible post-measurement states, and they are distributed according to a probability distribution P of AI. So this is what describes the post-measurement ensemble for this example, right? Now, one way to describe it is as a convex sum. So now I'm going to describe this by the following, in the following way. So I'm going to call this this post-measurement state as rho, okay? And I'm going to say that it is a collection of projectors, okay, onto these pure states, weighted by these probabilities, okay? So if I want to expand this out, I'm going to say this is of the form P of A1, 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 P of A2, etc. If it's a d-dimensional space and it's a d full rank observable, then this is. Okay, so this is what is called a convex mixture of pure states. So now I'm going to contrast for you this idea of pure versus mixed states. Okay, so the states that we have been describing so far as vectors in some Hilbert space, these are the pure states, right? Mixed states are essentially mixtures of pure states. That's quite intuitive, right, from the name. But what does one mean by a mixture? This is what one formally means by a mixture. And why am I calling it a mixture and not a combination? Because it is not a linear combination of pure states. So please note immediately that if I write down sum over I, Ci ket Ai, okay, what is this? This is some superposition of the eigenstates. Right? And this I'll call some state phi. Now this is still a, what kind of state is this?
Pure.
Indeed. Indeed, this is still a pure state. Okay? It's simply expressed now as a coherent superposition of the eigenstates. Coherent because there is some coherence information that is hidden in these coefficients Ci. In particular, you know, these are complex coefficients, so they actually carry some non-trivial phase information, right? These coefficients. But now look at this description, okay? This is not a superposition. First of all, what kind of object is this? Is this even a vector? Is rho a vector?
Matrix.
It's a matrix. It's an operator because it's essentially a sum of such rank 1 projectors, right? So rho is an operator, okay? And because, so the way I'm motivating the density operator description is to say that you want to find a way to describe the post-measurement state in general, right? Now, if you know what the outcome is, which is you know that you realized the ith outcome, which means you observed that this observable had took on value AI, right? Then you know what the post-measurement state is. But so the way people sometimes describe the density operator or the ensemble picture is to say that it is the post-measurement state when you don't know the outcome, right? How do I describe a scenario where I'm measuring observable A on state psi, but I don't want to describe the outcome every time I want to describe the post-measurement state? I want to give a description which encompasses all possible outcomes and all possible post-measurement states. Well, you describe it by an ensemble. The outcome is a set of states now, which is the set AI, which occur with certain probabilities pi. How will you describe this situation? This is not a situation where the outcome is in a superposition of the AIs. Each instance of this measurement is giving you a different state. It's giving you a different realization, right? So this is clearly cannot be expressed as a superposition of these states. Rather, it has to be an incoherent mixture. So there is no relative phase information hidden. It's simply a convex sum. Why convex? Because these are positive numbers, right? These PAs are some numbers which lie between 0 and 1. Okay? So it's simply a weighted sum of a set of states. But if I cannot describe it as a vector, right? Because it's not a superposition. So rather, I describe it as a collection of projections weighted by the corresponding probability distributions. So now I have moved from a vector description of the quantum state to an operator description of the state, right? And this is the reason I wrote the measurement transformation like this. I had to convert this vector to an operator. And what is the so-called operator associated with the state psi? It is its own projection operator, right? So this get psi psi. So let me write that. So I started by writing, okay, so let me just note here that rho is not a superposition state. Rather, it's an incoherent mixture. It's an operator that describes mixture of pure states. Okay, so now if I have a single pure state, what is the density operator associated with it? So if I have a single pure state psi, then the associated density operator is simply the projector psi psi. Okay, so this operator is what's called the density operator. I don't know whether I said that in all the things that I said. So this is what you call a density operator. Okay, it's a specific kind of operator that describes quantum states. Now we'll see what are the special properties that it needs to have. Okay, so and this operator is what's called the density operator, like I said. So let's also note here that pure states, okay, so let me note that here. Okay, so I hope this is clear that if I have a single pure state, then the associated density operator is simply this, right, which is the projector onto the pure state, right? But if I now have a mixed state, right, then what it means is I have, so now I'm going to move beyond just the measurement description, because obviously the density operator framework is a convenient way to describe any such situation where you have a collection of states, collection of pure states with certain probabilities. For example, in a quantum communication setting, I want to say that, so even the two-party game that we discussed, where Anita is sending one of two states to Bharat, right? How would you describe this, the input to this protocol? You would describe it as an ensemble of two states, ket 0 and ket plus. Let's say she's picking them, equally at random. So then the corresponding probabilities are simply half and half. So that would be the ensemble half 0, 0 plus half plus plus, right? So in general, a mixed state is a set of probabilities associated with a set of pure states, or rather a set of pure states occurring with certain probabilities, right? And the associated density operator is then sum over I, Pi, psi, the projection onto psi. So the single pure state case is a special case of this, where you have only one state in the ensemble and that state is occurring with a probability 1, right? So what are the properties of the density operator? So we saw already that obviously this is now a matrix, right? So this is a matrix on the Hilbert space of the system. It is no longer a vector in the system space, it's rather a matrix on the system space, okay? And what are its properties? So what kind of matrix is this? So let me ask you, we've discussed various classes of matrices, right? So is rho Hermitian?
Yes, ma'am.
Why is it Hermitian?
Ma'am, all the PIs are real, and the projector means each projector operator is a Hermitian. So it's a combination
Very
of
good. Yes, indeed. So when I take rho dagger, right, then you realize that, okay, these PIs are, remember, probabilities. So sum over I PI is 1, and they're all, excuse me. So the PIs are real, and indeed they're actually positive numbers. They're more than real, right? They're actually positive numbers, right? They're probabilities. And what's more, these are projection operators onto a particular pure state, psi I, right? So rho dagger is the same as rho. It is Hermitian. But it is more than Hermitian. It is a special class of Hermitian operators. Can someone think and say what special class it is? So what happens?
positive operators. Positive operators.
Indeed, yeah. The rho are positive operators. So how would we show that? So let's take the expectation value of rho with respect to some state psi. Okay. Let me take the expectation value of rho with respect to some other state psi. Sorry, phi. Right. So then what is this? Phi sum over I pi psi phi. So you know that I can pull the sum out, right, of this inner product operation. So then I end up with phi I psi phi. Now psi I phi itself is complex in general, but this is the complex conjugate of that. So what is this now? This is sum over I pi modulus of phi psi I squared, right? These are all real, positive, right? These are positive, they are mod squared of something. The PIs are all positive. So this entire sum is a sum of positive terms and it's positive. And so this is true for all states phi. Okay. And when this happens, you know that rho is a positive operator. The third property that will be of interest to us is the trace of rho. Okay. So can someone evaluate for me what the trace of rho is? As I've often said, pick some orthonormal basis. By the way, I should mention here, okay, just note for a moment, this mixed state description that I wrote down does not necessarily require that the psi-i's be mutually orthogonal. The psi-i's need not form a basis. The particular example of measurement, this ensemble had a set of pure states which were mutually orthogonal, namely the eigenstates of an observable. Okay, but in general, the density operator could be a mixture of any set of pure states. Okay, so let me note this here, that the psi-i's need not be orthogonal. They need not be mutually orthogonal. This need not be an orthonormal basis. It could be any set of pure states. Okay, we'll see some examples shortly. So what is a trace now? And how do you evaluate the trace? You pick some orthonormal basis. I'm going over these steps for those of you who are not familiar with this. So please do this with me. So pick some orthonormal basis with elements, let me call this Ej now. Okay. So then trace is nothing but take the diagonal elements of rho and sum over them. So please evaluate this and tell me. What is this? Are people
We
working?
sum over J first, since the ket psi-i's are normalized, this will be just the mod square of the sum of their coefficients in the basis EJ.
Okay,
So
which
it
is
will
what?
be
Yes. And then, okay, good. So what is the final answer, you tell me, and then we'll
1.
explain how we get that. The final answer is indeed 1. And how we get that is you do the sum over J first, right? So then you have sum over I pi, sum over J, Ej psi I mod squared. But what is this? These are nothing but the coefficients, the mod squared actually of the coefficients of psi I, of each psi I in the basis Ej, right? So I'm just going to say that this is 1, since psi I are all normalized pure states. I mean, the normalization is just assumed when I say pure, right? So this is 1. And so I am left with the sum over I of pi, which is 1. So trace rho is 1, and this is a property that holds for any density operator, right? The only thing I said is that it's a convex sum of pure states, right? So the trace is 1 holds for any density operator, okay? So now, by the way, is there another way that one could have shown that the trace is 1 even more simply? So let me tell you another way of showing this. Because you guys have to get familiar with doing this bracket algebra the rest of the course. So what is trace rho? This is trace of, I'm not going to expand it in any orthonormal basis and all, okay? So I'm just going to write sum over I, pi psi psi, okay? Then I'm going to say that I pull the sum out. I pull the pi out, that's just a number. So it's essentially sum of the traces of each of these pure states, right? So now what is this? What is trace of each of these pure states?
One.
Indeed. So the trace of each of these is simply, remember I told you this trick that when I just have a projection like this or onto a single state, there's a projection on a single state, right? Then the trace is nothing but this inner product psi, right? When I just have a single outer product and I want to take its trace, that simply becomes the inner product. This is a neat trick to know and also check for yourself that this holds again by putting an orthonormal basis and so on. So, but inner product of psi I with itself is 1. So this again becomes sum over I pi, which is 1. Okay. So now we are ready to formally define a more general description of a quantum state. So now we are going to have a modification to postulate 1. So this is what I call a modified postulate 1, where we said quantum states are simply vectors in a linear vector space, complex linear vector space with an inner product. Now I'm going to say quantum states are described by or associated with or whatever density operators on a Hilbert space. And what are density operators? They are simply operators which are positive semi-definite with trace 1. Okay. The way I arrived at this, these two properties, so they're positive semi-definite and trace 1, is by associating a certain ensemble of pure states with it. Now we can do the converse, right? So I can make this like a little theorem or a lemma which says the following, that rho is associated with an ensemble of pure states Note that I'm just saying pure states. So I'm not saying anything else about these states. They don't have to be mutually orthogonal. I'm constantly repeating this. They don't have to be. They could be, but they don't have to be. Okay. Rho is associated with an ensemble of pure states pi psi I if and only if, okay, these two properties are satisfied. That is, it is positive semi-definite and trace rho is 1. Okay. And remember that these pi's are probabilities, so they sum to 1. Okay. All right, so we just showed one part of this statement, right, where we said if you have an ensemble like this and you describe the rho in that form. So I should say when I saw associated with an ensemble, how do I associate it in a particular way, right? Which is I make this convex sum say as rho is equal to sum over I pi psi, right? If and only if these two properties are satisfied, right? So we've already shown the first part in some sense, which is that if rho is described like this, then we have shown that it must be positive semi-definite and it has trace 1. Now, how do we show the reverse, which is the only if part, let's say? So given a positive semi-definite trace 1 operator, how do you associate an ensemble with it? Where is the point coming from? Can everyone? Okay. Okay, I'm just going to mute everyone. Okay, is that better? All right. So given a positive semi-definite trace 1 operator, how do you associate, or is there a natural way to associate always an ensemble of pure states with this operator? Please unmute yourselves and answer if you wish to answer. Think about it. Is there a natural way to associate an ensemble of states with such an operator?
Ma'am, diagonal elements uh, are the probabilities of those n basis states, right?
Yes, but why do you get basis states and diagonal elements being probabilities in this case? Correct. You're indeed right. So what is a key property you're exploiting? So there are two properties here. The fact that it is positive semi-definite means it is Hermitian, right? Because positive semi-definite operators are a class of Hermitian operators, which then means that it is always diagonalizable, which then means that I can always expand rho in terms of its eigenstates. Okay, I'm just going to call them EI, okay? And eigenvalues, right? This is the so-called spectral decomposition. But remember that this is the special case where the lambda i's are all positive. Okay, so don't immediately go back and say, oh, but this is true for every Hermitian operator. But every Hermitian operator is not a density operator. The subclass of Hermitian operators, which are positive operators, and within that, the subclass, which has trace 1. So what does that property tell you? The trace 1 property then tells you that these lambda i's indeed form a probability distribution. Okay, so the natural ensemble to associate with every density operator, in some sense, is the eigenstate ensemble, which is the set of eigenstates of this density operator weighted by lambda I, because you know that you can always express rho via spectral decomposition in this form. Okay, so I hope this reverse argument is also clear, and it is not a trivial statement to make. It's a slightly non-trivial statement to make, right? Because now you're saying both ways. So if I have a set of pure states and probabilities and I express them like this, convex sum, then that gives me a special kind of operator on the Hilbert space with these special properties. Conversely, if I have this special kind of operator with these special properties, I can always express it as a convex sum like that. Okay, so this is the idea of a density operator, and this now, like I said, generalizes our description of the state, and it is a somewhat necessary tool for us if we really want to describe the complete set of transformations, which includes things like measurement. Okay, so now you see you can describe measurement as follows. So anyway, that sort of concludes the definition and discussion of density operators. So how does one describe the measurement transformation now? Let's say we started with a pure state, okay, which is this psi, and there's some observable A, and you get one of a set of outcomes. Now I can describe this as a map on density operators, right? Because the outcomes, you know, are one of these set of eigenstates. So what is this map? So this is the initial density operator, correct? Like I said, this is simply the density operator associated with a single pure state. Now, what does it mean to say density operator associated with a single pure state? Physically, what kind of scenario is it capturing? It is simply capturing a scenario where the same state is being prepared many times, which is, if you think about it, the statistical description of measurement, right? It's as if you prepare the same state multiple times and then do this measurement repeatedly on these different copies of the same state.
Okay, Mama. Okay.
I'm not able to mute this person also.
हरशी आम्ही आता बुरशे करता ग
ना सांगता रे
पूण आपुणून बुरशे आता आम्ही काय करिना ते बारीक बरे बुरशे करून हांव हांगा दीस बरे हांगाच बसून आसता
आपल्या काय ना उमळ
भुता मरे ती सद्दा
आणि कुत्र्याची चादर उमळले आहे कुत्र्याचं
माझी 5 ते 6:30 एक्झाम आहा
टाको नका
सांगता तुका नाका आले काय
Not even able to see who is talking.
कुत्र्या निवळ डोरा कशी आता माझी एक्झाम
म्हणजे काय
म्हणली ना म्हाका अभ्यास करू नाका आता गो क्लास या म्हाका अभ्यास करून टाइम नाका
Guys, are you able to see where this noise is coming from?
बरं सांगलं असे बेजार जाण तापोन सांग बाबू आयज कुत्र्याक नाडोया कोणी आमच्यान नाडोया तेका म्हाका चाक करून घालला तो बाबू कुत्र्याकूच लागून सोडून तुका बाय काय म्हणलं नावे ना
Vaibhavi, can you please mute yourself? Okay, she's exited the call. All right. Sorry, let's proceed. Okay. So the single state, pure state, being associated with the density operator kind of describes a preparation scenario in some sense, where the same identical state is being prepared many, many times, right? Which is how the which is what a measurement description is in some sense, if you want to talk about the statistical picture, right? Which is, like I said, you don't want a description which with reference to a particular outcome, but it's as if you don't know which outcome occurred and you want to describe this transformation, right? Okay, so this row then goes to, let me just complete this and then can ask you a question. So this row goes to sum over I, pi, rho pi, divided by the associated probabilities, right? That's what I said. So I have trace pi rho. Okay. So remember earlier I had just put a single pi and I had said corresponding to outcome I and so on. But now I can go ahead and do this, right? Where I can now say sum over I pi rho pi by trace pi rho. Just make sure that this gives you the correct ensemble. Remember in the ensemble picture, what should this look like? This should look like probability of AI, right? So does it look like that? Let us just check this out, okay? So this is now sum over I, AI, psi, so it becomes mod psi squared, and there's another AI sitting here, divided by the mod AI squared. So actually I should not divide by these probabilities here if I want this description. Yeah, so that's the reason I wanted to write this out. Yes. Okay, so this is how I want to describe this transformation, like this. See, in the earlier case, I was trying to describe a collapse, right? And so there I had to divide this by the probability. So I had to say pi, psi, pi divided by the corresponding probability, right? This was the earlier description that I had, but this was with reference to a particular outcome where I wanted to describe the collapse. But now I want to say it is one of these possibilities, each occurring with a certain probability. So in some sense, I'm multiplying with the corresponding probability again, and so this denominator goes away. So what I end up with is just this, which is indeed the same as P of AI. Okay. So what is the question? Yeah, okay, that's okay, Vaibhavi. Yeah. Just be careful in class from now on. Yeah. There was a question. Was it Neelkant or somebody else?
Yes, ma'am, it was me.
Yeah.
Actually, I got confused when you started this thing. Rows was precise. You said statistical description, and I.
Yeah.
Sorry.
What's the confusion?
I mean, what I could understand that initially, when we were describing state and transformation and collapse and all these things. So we were saying it in a very verbose way. Okay, when something acts on that state, it collapses to this state. now we are in a way defining it in a more concrete mathematical way, where this summation representation in a way tells us mathematically that for a given state, these are the possible outcomes with these probabilities. I mean, this is what I could understand from this.
Yeah.
Hello? Hello?
Correct. Yeah, that's exactly what we do. That's it. But I'm trying to reinterpret this again, and I'm saying that, yeah, another question. Okay, so what I'm yeah, your
Hello, ma'am.
description is
We can't hear you.
collapse postulate in word. So now a formal mathematical description. This is what it is now. The measure transformation. We discussed. Is it better? Oh, I see. Guys, can you hear me better now?
Yes, ma'am.
Yes, ma'am.
Okay, so it's more stable now?
Yes, ma'am. Yes.
Yes.
All right, good. Okay, so I think there was some temporary network issue there. Okay, so yeah, I think whatever you said is correct. And we were describing this somewhat informally, the whole collapse idea. Now we have made it more mathematically precise. And we have made the idea of a measurement transformation also mathematically precise. Okay, so now what have I said? I've said measurement is a map on the set of density operators, which means the measurement is a map that takes density operators to density operators, right? So remember earlier we had only dealt with transformations that take states to states. Those are your unitary transformations, right? Those are the quantum gates. But now we are talking about something which is taking density operators to density operators, right? So it is now a map on operators to operators, on matrices to matrices. Okay, and how would you describe that? So such a map is described by a collection of operators. So if it's a projective measurement, it is a collection of projections such that rho goes to sum over I, pi rho, pi. Okay, and this I was just trying to justify here by showing that these two are the same. This justifies various hand-wavy things we have said, right? We have said the post-measurement state looks like this. Now you see formally the post-measurement state looks like this because I have defined this as a map pi rho pi. And so formally the post-measurement state looks like a collection of pure states weighted by the probabilities, right? So, and of course that then guarantees that it's a density operator because you can of course check that the final state has trace 1 and is a positive semi-definite. Okay, so this kind of completes the picture now. That measurement is no longer some mysterious collapse. It is a well-defined mathematical map from density operators to density operators. Now, all that I was trying to say was, what does it mean to say the initial state is associated with the density operator? What is the ensemble there? For the final state, it's clear that it's an ensemble, right? It's one of a different set of outcomes weighted with certain probabilities. So what is the initial ensemble? So often in the literature, you will find that this is called the preparation ensemble. And the preparation ensemble in this case, it's just preparing the same state many, many times, right? It's just an ensemble which comprises of the state psi every time the state psi is prepared. With what probability? Well, the same probability. Consider a different scenario, like where there is a two-party game that Anita and Bharat are playing. So what is Anita's preparation ensemble? What is her ensemble in that case? What is the ensemble that's being prepared? Yes?
1 by 2
Some P.
plus 1 by 2 plus
Indeed. Yeah. So it's the state 0 or the state plus, each prepared with probability half. Okay?
Excuse me, ma'am.
So, yeah.
I mean, should we associate a half probability with each of the state?
That depends on how she prepares it. I'm assuming that she's preparing them, picking them equally at random. Like each time she tosses a coin and she decides whether to prepare 0 or plus.
But
Before every
sorry.
Yeah, that's all. So before every preparation process, she tosses a coin. Okay, if it's head, she'll prepare ket 0. If it's tail, she'll prepare ket plus.
So technically, I can also associate a set of probabilities with my preparation ensemble as well, right?
Indeed, yeah. So you will find that in typical information theory settings, I don't know how much information theory we'll get to cover in this course, but in an information theoretic setting, there will be some set of pure states that you want to pick. So I'll give you another example of from quantum cryptography, let's say, from what is called quantum key distribution. Okay. So there, in this two-party setting, one of the two parties, let's say A, prepares this set of 4 states, okay? 0, plus, 1, minus. And each of this is prepared equally at random. So then the ensemble would be, or the density operator would be this, 1 by 4, ket 0, 1 by 4, let me put a comma here and a semicolon here. So let me just write down this in this picture, right? So it's basically going to be 1 by 4, 0, 0, plus, plus, 1, 1, minus, minus. So this is a classic example where you don't need these states to be orthogonal, correct? You see that actually 2 of them have overlaps, these 2 have overlaps, these 2 have overlaps, right? But you're guaranteed to satisfy the properties of a density operator. The trace will be 1 because each of them is a trace 1 object. You're summing 4 of them and you're dividing by 4. Trace 1, and they're all positive semi-definite. So this is guaranteed, right? So this is an example of a typical ensemble that you may construct in a quantum communication scenario. Okay. So yeah, I mean, you can think of different preparation ensembles, right? And in this case, the input that comes to the second party, which is Bharat, is itself an ensemble like this. So now you kind of add layers. Now the measurement description has to account for the fact that the input is not simply a pure state, but it's well and truly a mixture of states. So that's where this transformation comes in handy then, right? Because now you simply have to take this input ensemble and apply this transformation to understand what's happening post measurement, right? Okay, so I hope you understand the need for the density operator description and how that fits into the examples that we've studied so far and how that fits into the measurement postulate itself. So one final thing I want to say before I wrap up today's lecture is the sort of mathematical difference between a pure state and a mixed state, right? So how do I identify whether a given state is pure or mixed? Okay, so note that trace rho is always 1. That is from the definition of a density operator. But what about trace of rho squared? Okay. So now consider 2 scenarios. One where rho is simply the density operator associated with the pure state. Okay. And one where rho is the density operator associated with a mixed state. Truly a mixture of states, right? So let's call this rho 1 and let's call this rho 2. So what is trace of rho 1 squared?
Same as trace of rho, which is 1.
Indeed. So this is same as the trace of rho 1, which is 1. Why? Because this is a projector. Projectors square to themselves. Correct? This is a projector onto a pure state. So you can see that trace of rho squared is nothing but trace of psi the whole square, but that's nothing but trace of psi, which is 1. Okay. What about the second case now? So what about trace of rho 2 squared? So let's work this out. This is trace of sum over I, pi, psi I, okay, times sum over j, pj, psi j. Okay. So the main thing to note, of course, you can evaluate this. This will be a double sum. You'll have pi, pj, and you will have these inner products. So basically, it will look like this. Okay. What does it look like? Note that this quantity is in general going to be strictly less than 1, right? Because each of these is something that is less than 1, right? Even if you assume the very specific case, so let's assume even that you're in some diagonal description of the density operator. So let's assume that psi I, psi j is delta ij. Okay. So even if you assume that, then this becomes sum over I pi squared. Correct? And pi's are probabilities, numbers between 0 and 1. So this sum becomes strictly less than 1. Okay. So this is a way to test whether a given density matrix is pure or mixed. So trace rho squared is often considered a measure of purity of a density operator. Okay. So trace rho squared is 1 if and only if rho is a pure state. That is, rho is of the form psi. Okay. So let me stop here. I just want to leave you with some homework for you to think about. So question is, what is the density operator associated with plus plus? Okay. Please tell me this. And what is the density operator? And by this, I mean, I want you to write down the matrix for me. Okay. Which means I want the matrix form. Okay. And similarly, the density operator associated with this ensemble, which is half 0 and half plus. Okay. Find a way to describe this properly. So I want to say half 0. Okay. There's a comma here to say that 0 picked with probability half and plus picked with probability half. Please write down the two matrices corresponding to this, because I want you to see the difference between a pure state and a mixed state in the matrix formalism, in the matrix representation. Okay, let me stop here. Questions? Okay, so all of you know about the tutorial session that's happening tomorrow afternoon, right? And I guess you all received emails. The TAs are actually going to great lengths. Okay, they're actually doing separate sessions because of the size of class and so on. So please attend the session. Please make sure you've looked at the tutorial before that, worked it out, thought about it, so that you can come and ask them some meaningful questions, which does not include what is the solution to this problem. Okay. All right. So see you all on Monday.